Okay, so here we're going to talk about simplifying radicals. Now, before we can talk about that, let's just talk about what a perfect square is. So, I mean, you could read it right here. A perfect square is the square of a whole number. So if I take 1 and square it, 1 squared is 1. Let's just make a little list here. 2 squared would be 4. 3 squared is 9. 4 squared, 4 times 4 is 16. 5 squared is 25, and this list keeps going. So I'm just going to fit whatever I can on here. So let's see, we have 36, 49, 64, and I'm just going to write ... Okay, the list just keeps going. Okay, now, these are examples of numbers that are perfect squares. You could also have perfect square variables. So if I said to you, what is x times x? Well, x times x is x squared. If I said to you, what is x squared times x squared? So in other words, what's x squared squared? It would be x to the 4th. If I said to you, what is x cubed squared? So for example, I'm going to write this one out. If I said to you, what is x cubed squared? Well, remember, when we have a power raised to another power, we multiply these. So I'm going to put x to the 6 on our list. Okay, so continuing with that trend, if I said to you, what is x to the 4th squared? Again, when we have a power raised to another power, we multiply these. So that'll give us x to the 8th. All right, keep going. What is x to the 5th squared? That'll give us x to the 10th. And if you notice the pattern going on here, I mean, basically, any even exponent is going to be a perfect square. So if I wanted to put the next, it would be x to the 12th, and then x to the 14th, and so on. So for any of these variables with the exponents on it, if I wanted to take the square root of it, so for example, let's just take a look at this one right here, x to the 10th. If I wanted to take the square root of x to the 10th, all I have to do is take this exponent and divide it by 2. Just cut it in half. So the square root of x to the 10th would be x to the 5th. And again, the reason for that is because x to the 5th, when you square it, is going to give you x to the 10th. Okay, so I know I already said this, but I just want to write down that basically your variables here are perfect squares as long as they have even exponents. So in other words, the exponents are divisible by 2. Okay, they divide evenly by 2. All right, well, let's take a look at some examples where we're going to have to simplify radicals. Now, if you look at number 1, all right, 75 and x to the 9th, those are not perfect squares. Those are not on the list that we just made. So what you're going to want to do is you're going to want to take this and break it up into 2 separate square roots. And what we're going to do is we're going to put all of our perfect squares under this first radical, and what we're left over with, all of our non-perfect squares, under the second radical. So if you look at a 75, what you want to do is you want to say, well, what's the biggest perfect square that divides evenly into 75? Well, 25 is. So I'm going to take 25 and put it in my perfect square radical. And since 75 divided by 25 is 3, 3 is what goes as our leftover in the non-perfect square radical. Now, x to the 9th, even though 9 is a perfect square, okay, we're not looking at a number, we're looking at a variable raised to a power. And remember, we said that in order for it to be a perfect square, it has to have an even exponent, which this isn't. So what you want to do is you want to take out the biggest perfect square that you can out of x to the 9th. So the biggest perfect square that you can pull out of an x to the 9th would be x to the 8th. And that would leave you with 1x left over to put into our perfect square radical. Okay, so now let's just simplify. So the square root of 25 is 5. And the square root of x to the 8th, remember, you just take the exponent and divide it by 2. So it would be x to the 4th. And then whatever's in this radical, nothing is going to simplify because we've already taken out as much as we can out of the radical. So you're just going to take that and bring it right down. So there's our answer. Okay, let's take a look at number 3. Let's do it again. So now as we look at number 3, you can see there's some things under here that are perfect squares, but not everything is. So we're again going to break this up into 2 separate radicals, our perfect square radical and our leftovers, our non-perfect square radical. Okay, so if you want to look at the number 48, now there are a few different perfect squares that divide evenly into it. So for example, 4 is a perfect square. 4 times 12 would give you 48. But we want to find the biggest perfect square that divides evenly into 48. So the biggest perfect square that divides evenly into 48 is 16. And since 48 divided by 16 is 3, we're going to put our 3 in the leftover, the non-perfect square radical. All right, so now if we look at x to the 5th, this is an odd exponent, so it's not a perfect square, but the biggest perfect square that we could pull out of there is x to the 4th, leaving us with an x left over here. Our y to the 4th and our z squared, those both are even exponents, so we can put those entire terms into our perfect square radical. So we're going to have y to the 4th and z squared. There's not going to be any left over in our non-perfect square radical because these are perfect squares. Okay, so the square root of 16 is 4. The square root of x to the 4th is x squared. Remember, you divide the exponent by 2. The square root of y to the 4th is y squared, and the square root of z squared is just c. And from here we can bring down our radical 3x, what's left over. So there's our answer. Okay, and the last one we're going to take a look at is number 5. This negative 4 in front, we're just going to take and bring right down. And since not everything in here is a perfect square, we're going to take it and break it up into 2 separate radicals. Okay, just like the last problem, I mean, there's more than one perfect square that divides evenly into 32, like 4 and 8. We could break that up in 2, but it's not the biggest perfect square. The biggest perfect square that divides evenly into 32 is 16. So I'm going to put a 16 here, and since 32 divided by 16 is 2, we'll put the remaining 2 over here. All right, x to the 7th, we have an odd exponent, so it's not a perfect square. The biggest perfect square that you could pull out of that is x to the 6th, and that would leave us with 1x remaining in our leftover radical. All right, y to the 8th, that is a perfect square because 8 is an even exponent, so I'm going to put the whole thing right here. Z to the 15th is not a perfect square because 15 is an odd number. So the biggest perfect square you could pull out of z to the 15th would be z to the 14th. And that leaves us with a z in our non-perfect square radical. Okay, so what I'm going to do is I'm going to bring this negative 4 down, and I'm going to open up a parenthesis, because what we're really doing here is negative 4 times this radical. So let's break down that radical. The square root of 16 is 4. The square root of x to the 6th would be x cubed, right, because we divide the exponent by 2. The square root of y to the 8th would be y to the 4th, and the square root of z to the 14th would be z to the 7th. And I can bring down the rad 2xc. Now, even though this 4 right here, even though this is a perfect square, I don't want you to say, oh, the square root of 4 is 2, so let me bring down a 2, because this 4 is no longer under a radical, so don't try to take the square root of it again. But what we are going to do is we're going to multiply this negative 4 on the outside of the parentheses. We're going to distribute it into the parentheses. So negative 4 times 4 is negative 16. So we're left with negative 16 x cubed y to the 4th z to the 7th, and then you can bring down the radical 2xz.